Welcome to the first video in our Class 7 series of instructional videos for notes. We ended our Class 6 looking at cyclopentane. So of course the logical next step is to look at cyclohexane. So cyclohexane has a ring strain of 0 kcals per mole, and perhaps this is why nature favors incorporating lots of 6-membered rings in organic molecules. We can see the bond line diagram to the far left top corner. Here is a chair diagram for cyclohexane where we've explicitly added all 12 hydrogens to the molecule and shown it in a three-dimensional sort of conformation. You can notice that there's no eclipsing hydrogen atoms. This is our most stable conformation for cyclohexane. Of course, it goes through different conformations at room temperature quite often, maybe 100,000 times or more, flipping between different chair conformers. So we'll look at that closely in the near future. So everyone needs to be able to draw a chair. It's kind of challenging. You don't have to draw a chair creating such relief structures for the bonds, carbon-carbon bonds in the front of the molecule. What's challenging about drawing a chair is appending the different kinds of hydrogens. Axial hydrogens are kind of easy. That is, they go straight up and down if you put an axis through the center of your chair cyclohexane, and there's one axial hydrogen on each carbon, and they alternate up and down. I think the more challenging part to drawing chair cyclohexane is appending equatorial hydrogens that sort of stick out from the equator of the chair cyclohexane. So let's look at that in more detail. Note, there are two types of hydrogen atoms, axial hydrogen atoms and equatorial hydrogens. Like I said, if you drew an axis through the center of the chair, you can see there are axial hydrogens that run parallel to that axis, one on each carbon, and they alternate up, down, up, down, up, down as you go around the ring. The equatorial hydrogens are a little more challenging to draw. I think the end ones are easy. At the tip of the chair, it points slightly down. At the foot of the chair, if it's like a long chair, it points slightly up. It's these ones on the side that are difficult, but here's a rule. This axial hydrogen here is parallel in terms of its bond to the adjacent carbon-carbon bond, not the carbon-carbon bond formed by the carbon to which it's bonded and the tip of the chair, but rather this carbon-carbon bond across the ring. You can see how those lines are parallel. Similarly, this axial hydrogen, its bond should be fairly parallel to the opposite side carbon-carbon bond. And you can see the same thing holds true here. This equatorial hydrogen is parallel to this bond, carbon-carbon bond across the ring, and this equatorial hydrogen bond is parallel to this carbon-carbon bond across the ring. So of course, practice helps. You'll probably be drawing a lot of chair cyclohexanes here soon. We have a few more pages of notes before we finish this particular video. Please bear with me. So I would ask, please do not write wedges and dashes to hydrogens in chair cyclohexane. It's already a three-dimensional model. And you can see in this chair structure, I've not, bold-faced the carbon-carbon bonds that are closest to us. All hydrogen atoms should have straight-line bonds, even though straight-line bonds and bond line implies that the bond is in the plane of the page. For chair cyclohexane, we already know that it's a three-dimensional structure, and to see groups on that cyclohexane ring, we prefer to see straight-line bonds. So wedged and dashed bonds are more appropriate for explicitly bond line diagrams, such as this form of methyl cyclohexanol. So there's no such thing as free rotation around a carbon-carbon single bond in a 6-membered ring. However, cyclohexane can assume different conformations through a series of small rotations in the carbon-carbon single bonds. We will look at that, especially in an energy versus conformational diagram in perhaps the next video. For now, I want to practice on drawing a Newman projection and then trying to convert a bond line diagram to a chair cyclohexane. So, as I said, first let's consider drawing a Newman projection for cyclohexane. Let's pretend I am these eyes sighting down these carbon-carbon bonds in my cyclohexane, chair cyclohexane molecule. You can see that I've drawn this hydrogen labeled A on the front carbon that my right eye is viewing, and this hydrogen attached to the carbon behind that carbon in front, which is equatorial, is labeled B. I've also numbered this carbon attached to this hydrogen in front on the right, labeled 1, and I've labeled this carbon in the back 4. So what would my right eye see? It would see a hydrogen coming straight down, of course the carbon directly in front of it, and HA would appear to be going up and to the right. Now, even though in the chair cyclohexane diagram HB appears above HA because of the way that three-dimensional structure is turned, in the Newman projection, where does HB appear? It appears staggered between HA and the hydrogen that goes straight down in front on the right. And that's because of the way this eye is sighting down that carbon-carbon bond. How about carbon 1? The carbon labeled 1 appears to go up and to the left. And even though the carbon labeled 4 appears to be above carbon 1 in the chair cyclohexane diagram, in the Newman projection it appears to be coming down and to the left on the carbon that's bonded behind the front carbon that the right eye sees. Of course, the left eye sees a hydrogen coming straight down, a hydrogen going up and to the left, and it sees carbon 1 coming up and to the right. It sees a hydrogen staggered, bonded to the carbon behind the carbon in front, according to the left eye, between the hydrogen and carbon number 1. And it sees a hydrogen coming down and to the left on the carbon behind the front carbon that the left eye views. And carbon 4 is coming down and to the right, bonded to the carbon behind the front carbon that the left eye sees. So note, all the hydrogen atoms are staggered. There's only one gauche interaction, but it's really not so bad. That gauche interaction in this Newman projection is between carbons 1 and 4, but as we'll see, the true gauche interaction of gauche butane comes from the interaction of hydrogens that carbons 1 and 4 actually don't possess in this, while they are bonded in the cyclohexane ring. Next, let's try drawing a chair conformation for cis 1,4 dimethyl cyclohexane. Why do I call it cis? Cis implies that those two methyl groups are on the same side of the plane formed by the cyclohexane ring. So they either get two wedge bonds or two dash bonds. That would be the same molecule. You just flip it over 180 degrees, and relative to each other they're located at the 1 and 4 carbon. Well, in this chair cyclohexane, if you're a little astronaut floating above this three-dimensional chair cyclohexane at carbon 1, you can see our methyl group is coming straight up. It would be the one that would be pointing up at you. At carbon 4, it's a little more difficult. While the methyl group at carbon 1 got the axial position, at carbon 4 it gets the equatorial position, but if you flattened out this ring, you would be able to see that these two methyl groups really are on the same side of the plane formed by the 6-membered ring. So just because a group gets a wedge or a dash doesn't imply anything about whether it is axial or equatorial in a given chair conformation. It's something you need to work out. This, of course, would be the same as this chair cyclohexane conformation where I've explicitly added hydrogen atoms to the other carbons, 2, 3, 5, and 6. You should try other isomers on your own. Of course, we'll have class time to practice. I think that pretty much sums up this video, and I'll see you in the next one.